Hi, welcome to Sunil Maths tutorial, Functional Analysis, class number 29. From this video, we learn Hilbert spaces. Let us see part 1. In the part 1, from video 1 to 28, part 1, in which we discuss Banach spaces. In part 2, from today onwards, from video number 29, we learn Hilbert spaces. And in part 3, we learn finite dimensional spectral theory. Up to now, we complete our videos up to part 1, Banach spaces. From this video, we learn part 2, which represents Hilbert spaces. So let us see the first definition, inner product space. Inner product space. Right. Let us take L of f be a linear space. L of f be a linear space where capital F is either the field of real numbers, or complex numbers. Either the field of real numbers or complex numbers. L of f be a linear space. F is either a field of real or complex numbers. An inner product on capital L. An inner product on capital L is a mapping. It is a function. It is a transformation. An inner product on capital L is a mapping from L cross L, means Cartesian product of L into itself. L cross L into capital F, which assigns or transfer to each ordered pair of vectors x comma y in capital L comma a scalar x comma y in capital F in such a way that let us see the first condition, in such a way that x comma y bar is equals to y comma x. Here x comma y bar is called conjugate complex of the number. Complex conjugate of the number x comma y. X comma y bar is equals to ordered pair y comma x. And see the second condition, alpha x plus beta y comma z is equals to alpha into x comma z plus beta into y comma z. And third one, ordered pair x comma y greater than or equals to 0 and ordered pair x comma x is equals to 0 implies and implied by x equal to 0. For x comma y comma z belongs to the linear space L and alpha comma beta belongs to capital F. Therefore, the linear space capital L is then said to be an inner product space. With respect to that specified inner product defined on it, defined on it. Let us see the definition of inner product space again, because it is very important definition in Hilbert spaces. So depends upon this inner product space, we learn Hilbert spaces. So let us see again. And L of F be a linear space. You know that linear space is nothing but a vector space. Linear space is nothing but a vector space. Where F is a field. It is a field of real numbers or field of complex numbers. It means this F is equals to either R or F is equals to C. Only either field of real numbers or field of complex numbers. Right. An inner product on capital L. An inner product on capital L is a mapping. It means inner product means it is a function. Inner product means it is a mapping. Inner product means it is a transformation. All are the equivalent words. I repeat. I repeat. Inner product. Inner product. It means it is a mapping. It is a mapping. Mapping means it is a function. It is a function. Function means transformation. It is a transformation. All are equivalent words. So, an inner product on capital L is a function that is defined from L cross L into capital F, where L cross L means Cartesian product of L into itself, which assigns or which transfer to each ordered pair of vectors x comma y in capital L to a scalar x comma y in capital F in such a way that satisfying three conditions: x comma y bar is equals to y comma x, alpha x plus beta y comma z is equals to alpha into x comma z plus beta into y comma z, x comma y greater than or equals to 0, and x comma x is equals to 0 implies and implied by x is equals to 0, where x, y, z they belongs to L and alpha comma beta belongs to the field capital F. The linear space L is said to be an inner product space with respect to this specified inner product defined on it. That's it. Now we learn something about these three conditions. Let us see one by one. Let us see. We learn three conditions here. The first one is known as complex conjugate. Complex conjugate. X comma y bar is equals to y comma x. Remember that. The first thing, in the above definition, in this definition, x comma y does not denote the ordered pair of vectors x and y, but it denotes the inner product of x comma y. I repeat it. Here, this one x comma y represents inner product. This is represents inner product, not an ordered pair. Inner product of x comma, inner product of the vectors x comma y. And remember that individually x and y they belongs to L, but this ordered pair x comma y belongs to the field capital F, satisfying the three conditions. So right, we name it the mapping. It can be assigned by the mapping. Name it as inner product. Right. So it read as this one read as inner product of x comma y. This one read as inner product of x comma y. Remember that. So right. If the field f is equals to R, then this inner product of x comma y is a real number. Is a real number. If the field is equals to C, then this x comma y, inner product of x comma y is a complex number. Is a complex number. The property in 3, I mean third condition. What is that third condition? Inner product of x comma y greater than or equals to 0. Inner product of x comma x is equals to 0 implies and implied by x is equals to 0. This is property number 3. This property number 3 is called property of non-negativity. Property of non-negativity. Remember that. This property, inner product of x comma y greater than or equals to 0, inner product of x comma x is equals to 0 implies and implied by x is equals to 0. This is known as a property of non-negativity. So right, let us see property number 2. What is property number 2 here? The property number 2 is alpha x plus beta y comma z is equals to alpha into x comma z plus beta into y comma z. Okay, this property is known as linear property. This property is known as linear property. Linear property. The third one is known as property of non-negativity and second one is known as linear property. Linear property. Now what about the first one? First property. The first property, in the first property, inner product of x comma y bar is equals to inner product of y comma x. So right, if the field f is equals to r, if the field f is equals to r, this property is called symmetry. This property is called symmetry. Symmetric property. If f is equals to c, it means if the field is complex numbers, if the field is complex numbers, then property 1 is called conjugate symmetry. The property 1 is called conjugate symmetry. So right. Now we learn 3 names for these properties. Let us see. Let us see. The first one, x comma y bar is equals to y comma x, is called symmetry property or conjugate symmetric property with respect to the field f or with respect to the field f as real numbers or complex numbers. Property number 2, it is called linear property. Property number 3 is called property of non-negativity. And this x comma y is read as inner product of x comma y, not ordered pair x comma y. This is read as inner product of x comma y. In case of real numbers, it is known as a real number. In case of complex numbers, this is known as a complex number. So let us see one more important point here. On R cube, R cube. An R cube means the set of all ordered pairs, ordered triads, the set of all ordered triads where x comma y comma z belongs to capital R. On R cube, there is an inner product which is called standard inner product or dot product defined in this way. Suppose for x comma y, like this, write the capital letters, x comma y belongs to R cube. It means x is an ordered triad alpha 1 comma alpha 2 comma alpha 3. Y is another ordered triad beta 1 comma beta 2 comma beta 3. Then the inner product of, we define the inner product of x comma y, the inner product of x comma y we define in this way: alpha 1 beta 1 plus alpha 2 beta 2 plus alpha 3 beta 3. This is known as, this type of definition is known as standard inner product, standard inner product over R cube, standard inner product over R cube. This definition satisfies all the three properties of inner product. All the three properties of inner product. So right, let us see. According to this is standard inner product over R cube. The same standard inner product over C cube is defined in this way. Inner product of x comma y is equals to alpha 1 beta 1 bar plus alpha 2 beta 2 bar plus alpha 3 beta 3 bar. This is known as standard inner product over C cube. So okay, up to here we learn inner product and some important points about it. Now we learn the very basic definition of Hilbert space. Hilbert space. It is a simple definition. If you know the definition of inner product space, then it is very easy to understand. A Hilbert space, a Hilbert space is a complex Banach space. A Hilbert space is a complex Banach space whose norm whose norm arises whose norm arises from an inner product that is in which there is a defined complex function. There is a defined complex function x comma y of the vectors x comma y with the following properties. Hilbert space is a, let us see, Hilbert space is a complex Banach space. Hilbert space is a complex Banach space whose norm is an inner product defined as a complex function x comma y of the vectors x comma y in the following sense are satisfying the following three properties. The first one, alpha x plus beta y comma z is equals to alpha into x comma z plus beta into y comma z. And the second one, x comma y bar is equals to y comma x conjugate symmetric property. And third one, x comma x, inner product of x comma x is equals to norm x square for all x comma y comma z belongs to H, and alpha comma beta are scalars. So by heart this definition, if you familiar with this definition, then obviously the next definitions and theorems are easy to understand. I repeat this definition. Hilbert space is a complex Banach space whose norm arises from an inner product, that is, in which there is a defined complex function x comma y with the vectors x comma y satisfying three conditions. The first one, inner product of alpha x plus beta y comma z is equals to alpha into inner product of x comma z plus beta into inner product of y comma z. Inner product of x comma y bar is equals to inner product of y comma x. Inner product of x comma x is equals to norm x square for all x comma y comma z belongs to H, where alpha comma beta are scalars. So before going to conclude this class, we'll learn a result and then we conclude it. If H is a Hilbert space, if capital H is a Hilbert space, then for any x comma y comma z belongs to H and alpha comma beta belongs to the complex number set of C, then x comma alpha y plus beta z, inner product of x comma alpha y plus beta z is equals to alpha bar into x comma y plus beta bar into x comma z. We prove this result. Let us see. We prove this result. X comma alpha y plus beta z can be written as, by using the conjugate symmetric property, alpha y plus beta z comma x whole bar, which is equals to alpha into y comma x plus beta into y comma z comma x whole bar. If you split the conjugate, you can write like this: alpha bar into y comma x bar plus beta bar into z comma x bar. Alpha bar conjugate of y comma x bar is nothing but x comma y plus beta bar conjugate of z comma x bar can be written as x comma z. This is the required property. Remember that inner product of x comma alpha y plus beta z is equals to alpha bar inner product of x comma y plus beta bar inner product of x comma z. That's it. In the next video, we learn some examples of Hilbert space.